some time, cures, and when you peel off, that is already carrying the pattern what you want. And you don't have to be using the hard master, you'll be using the elastomer to carry the ink further onto various substrates. You can do repetitive patterning using such elastomers. And there some conditions are written here. The friendly properties of PDMS are listed out there. And so this is one of the typical processes. You put the PDMS, these protruded features are coated with molecule. So wherever the protruded feature touches, like a stamping process only, wherever it touches the substrate, it will just dialogue with the substrate and transfer some molecules. And so you will have the molecules coming on top. They could be self-assembling monolayers. You could have simple thiols coated on PDMS, and PDMS will transfer onto silicon, right? So, and that you can take and manipulate and create lots of different features. These thiols themselves can be masking layer for the gold. You know that thiol molecules adsorb on gold, and wherever thiol molecule is there, gold doesn't like to get etched away, even if you dip it in etching solution. So you can exploit this combination of ideas and create some nice metal patterns or even semiconductor patterns. And the group which, this is from Professor Whiteside's group, they have pioneered this field way back in 1990s. They created lots of material patterning using soft lithography methods. Now we will move over to yet another technique. The soft lithography is good. It can produce, as I showed you, if you see the previous slide, you can see the patterns are of the order of, look at that, they are just inching towards nanometer. They are not yet entering into the nanoscale. So they're all restricted to around minimum feature size of the order of 5 micron, at best 2 micron. But you have not really made nanometric features. So better technique would be nano imprint lithography, which has come about in the last 2 decades. In this case, what one would do is create a silicon master. Instead of using PDMS, one would be using different types of thermoplastic polymers. And here you have, this is the master, which is coming onto a substrate coated with the this polymer, and then when you press it hard and also heat it up, you can see that the stamp is making penetration, and this polymeric layer is accepting it, and that's how you tend to create features here. Okay, these are very specialty polymers because they should not undergo distortion as you take away the stamp itself. So there are a lot of practical issues there, but nonetheless people have standardized these techniques, and see the way the patterns have been made. Whatever you did on a silicon master down to say 30 nanometer, those features are reproduced in this case. You see here on a large area, right? There are such examples in the literature to create very fine features. And it's also adaptable for roll-to-roll processing. You can see sheets of flexible sheets done where patterning has been done down to 30-40 nanometer length scale. So nano imprint lithography is quite a successful method. Once you optimize the condition and set it, and it keeps going even for rolls. People are producing rolls of materials with the nanometric feature sizes. Now we'll come to the last part of it, which also relates to my interest, my research interest, which is direct write nanolithography. So you have appreciated the difficulties with conventional tools now, right? So we'll now enter into something which is not very different from what is being done, but just that some cleverly twists are given to the lithography such that one could be realizing, you say for example using soft lithography method, can we create patterns which are even 50 nanometer kind of feature size. There we had seen 50 micron, 20 micron. Can we come down to say 50 nanometers? I'm going to show you all that is possible with some tuning of the recipe. Before we do that, take a look at this. Whenever you're trying to work on the resolution, trying to improve the resolution, you want to come down in this scale, right? You want to create finer and finer features. When you do that, the technique available in the literature, they offer you, smaller and smaller areal throughput. This is meter square per second. If you're using, newspaper printing, big roll can be printed in no time, right? Because the areal throughput is very high. But if you're writing with the STM tip, you come down to such small areas, but you're essentially having atom precision. So these are sort of standing as compromising. You are at a compromising situation now. All that would be required is stand straight here, you want to actually have very fine features, but with very high, so you want some techniques out here. I'm going to show you there is such possibility, okay? And that is also the current research field. I thought I'll give you some glimpse of what is going on more recently in terms of innovations in the lithography field. AFM is one possibility. You can use the atomic force microscopy tip as a pen and coat the tip and make it carry some ink. Then it is called dip pen nanolithography. The other one is actually use it as a conducting tip and burn local regions. Then you doing it by writing by local oxidation. So I will have some examples from both varieties. This is a technique which is pioneered by Professor Chad Mirkin at Northwestern University, wherein they realized that if you bring a AFM tip, common AFM tip, okay, close to a substrate, say mica or something which loves water but is not able to condense water for various reasons, if you polarize the surface, electrically polarize the surface with the AFM tip by holding it close to the substrate, you will have essentially nano droplets of water condensing there. A very early observation in mid-1990s, but they took it very seriously and actually exploited it in defining dip pen lithography. They made the tip carry molecules of interest and created a meniscus, right, on the substrate and started dropping molecules wherever you want. So AFM was taught, the tip was taught to drop the molecules in a given fashion, with which you can actually define very fine features on the pattern. So these are all the experimental conditions, okay? So let's not get into those details. The information is available in the slides. Look at the patterns here. So this is a gold surface onto which you have written with an organic acid, MHA. Fine features here. The feature width is of the order of 60 nanometer. It is going with the sharpness of the AFM tip, right? And in this case, this is 30 nanometer. So there are layers of molecules, right? You have ODT all over, and then on that, this is a thiol system. On that, you have written with an acid system. So chemically, the functionality is varying at the nanoscale, and you have a very fine control on that. And this is being practiced using dip pen lithography. Why it's called dip pen? Because the tip doesn't have a fountain behind, right? It doesn't have ink reservoir behind. You take the tip and dip it in a pot, typically some some porous, it could even be filter paper or something which is inked already. So you hold the ink in engagement with that kind of substrate. That's enough. It will pick up a lot of ink by capillary action, and with that you can go on writing long hours. Once you start writing, it's all there. Probably you are not able to appreciate that. The reason is, what is the width of the tip? You can imagine Mount Everest, right? If the tip of the Mount Everest is the AFM tip, you cut the Mount Everest at the bottom and hold it upside down. That's how AFM tip is working. So you can imagine the forests around there, the valleys around there, everywhere your liquid ink is hosted, right? Enormous ink is hosted, and at the nanometer pattern, you can the ink which is deposited so small, you can go on writing for long hours. And how do you write? As you engage the tip, the meniscus gets formed. It is a rather slow process. Couple of orders of in terms of time domain, it is much slower compared to the scanning itself. So it takes time to establish the meniscus. That's why you do writing very slowly. And once you are done with the writing, you can take the tip away and do scanning fast. When you are doing the scanning at a faster speed, you will not be able to establish the meniscus with the substrate, which is crucial in transferring the ink. So you can use the same tip for writing as well as imaging. That's the beauty. Okay, that's how dip and lithography techniques work. You can also image it later with a different AFM tip and whatnot. So these are some more chemical patterns which are created on the substrate, and in fact this field itself has matured now. A lot of variations have come about. I will not have time to get into those details, except that I want to show you that this is also very low throughput, because as I told you, you're writing nanometer feature and it is a serial process. And how to make it a parallel process? Again, there have been efforts to make parallel tip arrays. I think I have a photograph to show you. Before that, let me also tell you about local oxidation process. Instead of having an inert material making up the AFM tip, it is typically silicon nitride, which is electrically not conducting. If you have a tip coated with a conducting material like metal, then the tip becomes conducting. You can actually apply some voltage and hold it pretty close to a given substrate, which is also conducting, like silicon, for example, semiconducting. If you hold it close to substrate, even if you apply 1 or 2 volts between the substrate and the tip, the electric field intensity will be so huge that it can locally initiate a chemical reaction. When it initiates a chemical reaction, the silicon gets to burn. When it burns, it produces silicon dioxide. So these are the features created by holding the AFM tip close to the substrate with ambient supply of oxygen and water molecules. SiO2 patterns are written up here. These SiO2 patterns are hardly 2 nanometer in height, in thickness, and in width they resemble the diameter of the tip itself. So with such precision you can burn the SiO2 patterns on silicon, and you dip it in dilute HF, the SiO2 gets washed away. You'll have trenches which you could visualize in the silicon, not with naked eye, of course. You have to do AFM scanning again to see such trenches. This is a polymer wherein you have created a trench just by scratching. Such possibilities also exist with AFM. Yeah, this is the picture of parallel pen lithography. Instead of having one AFM tip, you can have millions of them and then make them go like this, so you can do faster writing. This also has been demonstrated. So trying to make AFM as a fast writing tool. Okay, I'm now with around 42 minutes. If you permit me, I'll go for another 8 to 10 minutes and show you some more recent literature results. See, all the while with optical lithography or electron beam lithography, we saw that we have been using resists which serve only as resists, right? Like PMMA or polystyrene. It is there to just transfer the pattern to the metal or a semiconductor, and they don't do anything else. Can we combine the functionalities? Why have an external resist and then use it to pattern the material? Why can't we have some ingredients which respond to photon beam or electron beam and get themselves patterned? You don't need an external resist. And with some process steps, you should be able to drive the system to the given chemical composition, right? So this is something which we have pursued, and I'll show you one or two results from what we obtained in the last several years. So this is a simple system, palladium alkane thiolate, and it tends to arrange into a bilayer system like this, very well ordered and in ambient conditions. So if you take palladium alkane thiolate and just spin coat it on a given substrate, it forms a smooth film, and this is how the alkane chains get to order. You can easily create a disorder in these alkane chains by exposing to weak, tiny bit of exposure to electron beam. Once you expose to electron beam, you can see the kind of defects which come about in the hydrocarbon chain, and by causing this kind of defects, you have decreased the solubility of the PD alkane thiolate. And having done that, it now starts working as negative resist, negative electron beam resist. All right? Yeah, so that is one process, and having done that, you can actually wash away those unexposed regions. So if you dip it in toluene for 5 seconds, unexposed regions wash away. These are easily solubilized, and then this stays on the substrate. So this can be very well done even on large areas, and you can see that having done that, there's one interesting chemistry step that is just gently heat it up. If you heat the substrate to, say, on a hot plate at 250 degrees centigrade, what happens is all these thiol molecules go away, and the chemistry tells us that PD gets reduced. Instead of PD2 plus, you now have PD, right? So by doing so, you have essentially realized PD nanowires here, down to 30 nanometer. So you didn't use a polymeric resist here. You avoided already 3-4 steps. At least 3-4 steps, right? You only coated directly the ingredient which is responding to electron beam and also easily converting itself to metal. But who asked you to restrict to metal? You can actually drive the chemistry further and turn it into much more complicated systems. This is yet another example taking another metal organic precursor. This is the tetraoctyl ammonium bromide, which is commonly used as a phase transfer agent for metal anions. And so you create these complexes. These are all very well known in organic chemistry. Just take this precursor and coat it on a substrate, and you see that you have created essentially electron beam resist with extreme sensitivity. The sensitivity here, which is expressed as microcoulomb per centimeter square, it is this number, but if you simply use the organic part itself without the metal, that also act as a, like PMMA for example, it has a sensitivity comparable to the PMMA or polystyrene, millicoulomb percent. So you gained on 3 orders here. So you can write much faster with this kind of metal organic precursors. And again, by gently heating or carrying out the chemical process, you will realize the final material in pattern. So I'll take you to another step. This is not by electron beam lithography, this is by soft lithography. In soft we learned that we'll have the microchannels, right, and raised patterns wherein you can host some ink. And why not we take again palladium thiolate and host it in these microchannels. This is a PDMS stamp on a silicon substrate, and as it is inserted inside, you just gently heat it up. You can have the chemical conversion, so you end up with strips of the palladium metal itself, right? This is done by soft lithography. But as you can realize, these are not nanometric features. Here you are standing at around 1060 nanometer. Can I bring it down to much finer features? Right, here it is. So what is done here is the stamp itself is made to collapse. The microchannel is made to collapse. This is 1 micron wide microchannel. You put some weight on top and heat it up, swell it up, do something so the microchannel collapses. When it collapses, you can actually confine the ink only along the edges, and that's how you have realized now much finer feature sizes, coming down to 50 nanometer.